Good morning to all of you. So today I'll be talking about asymptotic analysis of a boundary optimal control problem on oscillating domain. Okay. So the overview of my talk is first I'll give the domain description while we're going to pose our optimal control problem. And then we'll discuss about the problem, that is basically a Neumann boundary optimal control problem. Then we'll give the limit problem, that is basically the homogenized problem. After that, we'll give the convergence result. Okay. So first we'll see what is oscillating domain. So in oscillating domain, it has two parts. One is fixed part, another is oscillating part. That oscillating parts is depend on the parameter epsilon. So here you will see that for epsilon is equal to 1 by 5, we have 5 this kind of pillar. And when epsilon increases, the number of pillars going to be increased, and their width becomes smaller and smaller according to epsilon. So when epsilon is very, very small, it's look like that. And when epsilon is very, very small, it's feel like that upper part will fill by this kind of pillar. So what you're going to do, we're going to pose in epsilon level an optimal control problem there. That is basically boundary optimal control problem. And we'll investigate what will happen when the parameter epsilon tends to 0. So for proper setup, so this is our reference cell that I denoted by lambda, and this boundary I denoted by gamma. For simplicity, I am assuming for time being now that there is no interior flat part of the gamma. I mean, apart from this M0 and M0, there is no interior flat part. Okay, and I am denoting this upper flat part by FM1 and lower flat part, I mean this one and this one by FM1, and in between part of the boundary gamma I denoted by S. So what you do, like for example, epsilon is equal to 5, we scale it down in x1 direction and put it periodically on omega minus. And on this domain, we're going to pose an Neumann boundary optimal control problem. Basically, our control going to act on gamma epsilon. So, yeah, so for mathematical setup, so we are assuming epsilon is equal to 1 by m for m belongs to natural number. This gamma is basically a graph of a function eta going from 0, 1. And assuming C2 function, just for simplicity, it will work for piecewise linear function also, piecewise smooth function. And this gamma is the graph of eta, and eta epsilon is just eta of x by epsilon, and this gamma epsilon will be graph of eta epsilon. Okay, so the control set we are considering the L2 per gamma. So L2 per gamma is a periodic function on gamma. Basically, the gamma is defined by eta function, and eta is periodic, so we can extend periodically to whole R2. So in that sense, we extend our theta belongs to L2 gamma periodically to extended gamma. So that I called gamma, and theta epsilon is defined by tau epsilon times theta. But tau epsilon is the scaling factor. So you see the scaling factor. This is basically, that part is like order of 1. This part I multiplied to get a nice characterization. If you don't multiply, still it is okay. And epsilon to alpha, because our boundary measure are going to increase like order of 1 by epsilon. So in order to get uniform boundaries and all these things, we have to multiply this factor epsilon to alpha, where alpha is bigger than equals to 1. And according to alpha, if alpha is equal to 1 or greater than 1, we get different limit optimal control problem. Okay? So now this theta is defined on gamma. So to define on gamma epsilon, we have to scale it by 1 by epsilon. So this theta epsilon hat is defined by theta epsilon of y dash by epsilon, eta y dash by epsilon. Okay, so this theta is coming from L2 per gamma, and for each theta we have theta epsilon hat. And this theta hat going to be applied on the gamma epsilon as a like Neumann boundary condition. So this is our state equation. It is minus Laplace E epsilon plus E epsilon is equal to F in omega epsilon. And this is that control thing that we are applying Neumann control on the boundary, on the oscillating part of the boundary, that is theta epsilon hat. And we are putting these two conditions to get rid of the extra term while do integration by parts. This is not needed actually, just to avoid extra calculation. That's it. That is E epsilon is 0 on gamma B, and E epsilon is gamma is periodic. Okay. So the cost functional is for each theta, basically our theta is coming from a fixed reference cell. So for x theta, we are considering this cost functional, that is L2 cost functional. J epsilon, E epsilon theta is 1 by 2, integral omega epsilon, E epsilon minus UD, where UD are the desired state that we want to achieve, or like we want. And theta is the control, and this is the corresponding cost for theta. So the optimal control problem is find E epsilon bar, theta epsilon bar belongs to H1 epsilon. Here H1 epsilon is the solution space for this like elliptic problem, where like H1 epsilon is nothing but it is collection of all H1 function which are 0 in gamma B and periodic in gamma S, where gamma S are the side part of the boundary. Like this one, I call it gamma S. Yeah. So for each epsilon stage, we have an optimal solution, optimal state and optimal control corresponding to for each epsilon. So what is our aim? Our aim is to analyze the asymptotic behavior of E epsilon bar and theta epsilon bar while epsilon is very, very small. So to analyze the asymptotic behavior, so that usually what we do that we write the optimality system corresponding to this optimal control problem, and we homogenize that optimality system, and from that we'll achieve our limit optimality system. And from that we'll say that this is our limit optimal control problem, and we'll have the convergence of each epsilon stage problem to the limit system. Okay. So to do this, we introduce the adjoint stem. So corresponding to this optimal control problem, this will be our adjoint state. That is minus Laplace V epsilon plus V epsilon bar is equal to E epsilon bar minus UD in omega epsilon. And this is Neumann zero condition. And this is the zero condition and periodic condition. Yeah. So using this adjoint state, we can characterize our limit optimal control, using this adjoint state, we can characterize each epsilon stage our optimal control. So this subscript epsilon, lower subscript, actually denote that at each epsilon stage, this is our optimal control, which belongs to basically L2 per gamma, these things. So this is characterized by these things. So basically here we have to use a tool for unfolding operator in this kind of oscillating domain that is developed by Appan. And here from that unfolding operator, we derive the boundary unfolding operator for upper flat part and lower flat part, and for S, the inside between M0 and M1.
What is S?
S is the part which part of the gamma, which that thing only, not the flat part. Yeah. So we have already seen by Professor Guardiolo that upper part will be filled by this whole kind of structure. So in limit case, we are going to have a limit problem on this kind of structure. So this omega plus, which has filled basically by all the pillar, and omega minus is a fixed one. Okay. So in this domain, we're going to have a limit optimal control problem. Okay. So first, now we need some notation to introduce the limit optimal control problem. So for each x3 belongs to M0 to M1, we define hx3, that measure of the set x dash belongs to 0 on square, such that eta of x set greater than x3. Basically, that take slice and project in 0 on square and take that measure. And HM1, and for M1 and M2, it is exactly when it is like eta of x dash is equal to mi for I going from 0 to 1. Basically, this is the measure M1, where basically our graph is flat. Okay. And this gamma x3 x dash is that we have fixed referential and we have a level curve. So eta x dash x3 is a level curve, and omega x3 is that omega x3 is that this value, where grad x dash eta will treat it as a function, and gamma x3 is the measure on gamma x3 x dash. Okay, and our limit solution in space will be this one. Like we have in the limits case that x dash direction derivative will vanish on the upper part. So we're going to have this kind of anisotropic Sobolev space, and on that Sobolev space, because we have contribution from the oscillation. So this H factor, this is basically this one. We're going to this is the contribution coming from the referential in the limit space. Like hx3 is the measure. Like for each level, we have that the width of the referential. And this W omega is a Hilbert space, which is for this inner product. This inner product, this W omega is isomorphic to, if you remove H, it is also isomorphic to the usual anisotropic Sobolev space that introduced by Professor Guardiolo. Okay. So the optimal control problem is for alpha is equal to 1, for F belongs to L to omega, we go, so actually we have started an optimal control problem where control are applied on boundary, but in the limit case, we're going to see that this control problem as a like mixed kind of control problem where some control will apply on the interior and two control apply on the upper flat part and lower flat part. So for A belongs to L to omega, that is already given. So our control set like rho1, rho2 belongs to R and theta belongs to L to M0, M1. These are a control, three control. And the optimal control problem is find u bar, theta bar, rho1 bar, rho2 bar belongs to this solution space and L2 M0 M1 and R cross R such that these things hold. That is J of u bar, theta bar, rho1 bar, rho2 bar is equal to infimum of this quantity, where J is given by this cost functional, where ym1, y the measure of that set that corresponding to what is called, to parameters that flat surface. And you satisfy, now for theta belongs to L2 omega, rho1, rho2 bar, you satisfy this following state equation. You see that in upper part, we have that all x dash direction derivative has vanished. Only we have x3 directional derivative. And in the lower part, it is as usual. And in the epsilon stage, we have control problem, only one boundary. But you see here, we have a control problem in the interior, omega plus. And in the upper part, we have control rho2. And in lower part, that in the interface, we have this control, rho2. Basically, we're like controlling the jump between x3 direction of u plus and u minus. And as usual, you have u minus is equal to 0, and u minus is gamma is periodic. So this optimal control problem has a unique solution. Okay, so now we have to relate what is the relation between this optimal control problem and the epsilon stage optimal control problem. So the relation is given by this way. So for suppose our E epsilon bar and theta epsilon bar are the optimal state and optimal control in epsilon stage, and u bar, theta bar, rho1 bar, rho2 bar is the solution, the problem 2, that is a epsilon stage problem, and problem 4 that just we have defined optimal control problem for a limit control problem. We have this following convergence, that is E epsilon bar, basically E epsilon bar plus the restriction of E epsilon on omega epsilon plus, extended by 0, which converges to this quantity in L2 0 on square, H1 M0 M1. V epsilon bar tilde weakly converges to Hx3 V bar plus weakly in L2 0 on square, H1 M0 M1. Where, I mean, like, basically we have convergence in H1 in x3 direction and L2 in x direction, because we don't have derivative in x direction. And E epsilon bar minus converges to U bar minus weakly in H1 omega minus, and V epsilon bar minus weakly converges to V bar minus weakly in H1 omega minus. And U bar, V bar are the like adjoint state corresponding to limit optimal control problem. And for theta epsilon bar or optimal control, then theta epsilon bar hat, we don't have exactly the convergence, like weak convergence, because we are on the boundary. So we have this convergence. For phi belongs to H1 omega plus, this converges to this state. So this is for alpha is equal to 1. So now if you see the characterization, in the we have like epsilon to the power alpha minus 1. So when alpha is equal to 1, this term will disappear. But when alpha greater than 1, there will be some epsilon factor. So when epsilon tends to 0, we see that in the interior, there will be no contribution. Basically, the interior contribution is coming from that inside flat part between M0 and M1. So when if alpha greater than 1, this term will be vanished, and there will be no interior optimal control problem. So for alpha greater than 1, we have same optimal control problem, except that there is no interior optimal control problem now, because that thing is vanished because of the factor epsilon to the power alpha. And it satisfies the same limit state equation, but without that control. And we have only control on the upper flat part and in the interface, rho2. Basically, this thing control like x3 directional derivative and jump between x3 directional derivative between u plus and u minus. And we have, as usual, periodic condition. And in the same case, we have also that E epsilon bar and U bar minus are the optimal control and optimal state for epsilon stage, and U bar, sorry, there won't be theta bar, only U bar, rho1 bar, rho2 bar are the optimal control and optimal state for the limit control problem for alpha greater than 1. Then we have this convergence. Except that you see here, we don't have any interior term, like for theta is not coming here because of the factor epsilon to the power alpha. Yeah. Okay, so this, so the thing is that we have solved this problem by just directly applying the unfolding operator and all these things, boundary unfolding operator that will be discussed by its Ayapan. So this problem can be tackled by another method by just seeing our domain as different level. Like so what we do, we just, this is another way to view this optimal control problem. So in that case, if you see like that whole contribution, we are not able to distinguish like what part of the domain is contributing, like what part of the reference cell contributing what. But if you see our domain in this way, like what you do, we just slice it our domain according to the extremal value of eta in different level. Okay, so I'm not giving the details thing here. So what we do, we just slice our domain different level, and for each level we'll investigate our optimal control problem there. So we are going to have same adjoint system, and for each level we're going to have a different characterization, and we want to contribute to what is the contribution from each level. For that, we have multiplied different test function supported there and extended by 0 like this. So we'll get in a final state like a multi-seeded function space that was first introduced by Taras Melnik. So using that thing, so basically if you see that we divide our domain in different levels, in that case we have getting like different all kind of like some layers of level, because according to our extrema value of eta. Okay, and we'll get this kind of multi-seeded function, multi-seeded solution space. Now for each level, we have upper part, we have this equation, and lower part as usual. Okay, and yeah, and we have also the same kind of, the corresponding cost function will be this one, for if we view our domain as a multi-seeded level, and we have this kind of convergence. So basically earlier what we have epsilon bar tilde throughout domain, but what we do, we restricted this omega epsilon rk like for each branch, and we extended by 0, and according to that we'll get this kind of convergence, where hrk will be the measure of that particular corresponding to that branch. Yeah. These are the references. So this work appeared in Mathematical Method in Applied Science this year.